give you the excellent weld appearance. For the advantages, for sure, we require a good fixture. With no fixture, we cannot do it properly. And for sure, once we need to produce this fixture and other additional tool, high capital cost required for initial setup. But this one, like say, one-time operational cost. Once you have those facility, you can do it in a very cost-effective ways. In on the back side, we also have the exit hole, but some research are ongoing to eliminate this exit hole, or we can use like the wedges on at the end of the weld in order for us to remove this exit hole, or we just put a run off tab, yeah, to make sure that we can eliminate this exit hole. So we have some other research ongoing in order to prevent this exit hole lah. And also the last part is it is not suitable for irregular shape lah. Usually we have like a flat surface or like a tabular section. For me, I'm focusing on the tabular section instead of flat surface. Okay, this is the basic concept. As you can see, we have high rotating tool. So it will plunge through the material. Okay, so it causes the frictional heat to soften both sides, and due to the rotation movement and the movement of the pin, we join them together as one good piece. This is the basic concept of the friction stir welding. Okay, this is what we did in our workshop. So here you can, as you can see, we produce no fumes, no arc, and we use no filler metal in order to join these two parts of aluminum together. Okay, this one for my expert field. I'm focusing on this tubular joining process. So this is what we did in our laboratory. Can you see them? Nampak? Okay, for tubular section, we start and end. We start at the same point. We start and end the process at the same point. And then we need to offset the two. So we go to the next video. I don't think I need to show this robotics. So we go to the next type of welded joints. This is what we use. This is what we can found in a common welding process. So we have corner joint, lap joint, butt joint, T-joint, and also edge joint. So this joint, in order for us to produce this good joint, we need to make edge preparation, which is very time consuming. But by using this friction stir welding, we can use it straight away. So we don't have to prepare the edge. We don't have to prepare. We don't require edge preparation. If you want to proceed for the friction stir welding. So we have T joint. You can use it straight away. Corner joint, butt joint, lap joint. So this is how we do it. So as you can see on slide. So you can use. You can put the tool on top of that in order for you to join them together. And also this need to be aligned in like 40 degrees angle. Okay, this is the comparison between the common practice and then with the new practice. If we utilize friction stir welding, so it's very we shorten your time in order for you to skip the edge preparation process. This is facilities abroad. You can find it in NASA Space Center for them to beat the external time for their space shuttle, and we also have one in Timraya itself, the origin place for friction stir welding. They have also those capabilities, and this what um um I attach for. Okay, I'm also using facilities in to run my specimen, and also in Osaka. I also have like some experience in Rutherford Appleton Lab in UK. Okay, this is comparison how to run friction stir welding on plate and pipe. So for this is the difference. So for pipe joining, tools start and stop at the same point. So if you start over here, if you start here, so it will end here. So to complete the wet cycle. Meanwhile, for the flat panel, two will travel along the wet line from point A to point B, and both require backing plate. But we don't call it as backing plate for pipe. We call it as our internal support. So for flat panel, we require backing plate. For the tubular section, we require the internal support in order for us to run the friction stir welding successfully. And also both require a good fixture. And then with good fixture, then you can run for the better result lah. And the main difference between these two process is for the tool in pipe joining, you need to offset the tool a bit from the center line. If compared to the tool that we use in flat panel. For the flat panel, we need to tilt. We can go maximum of 3 degrees angle in order to get the better result. If not, you can get a wormhole inside the plate. So you will not get the proper joint. So this is the main difference between this flat panel and also the tubular section. So you need to be alert on the point number 4. Okay, this is how we tilt the tool. So this is the tilt angle. So I think the maximum is about 3 degrees. If you go more than that, you will cause the wet effect occur in your wet side or in your wetman. Okay, this is the difference between tilt angle and offset position on tubular section. This is tilt angle required for the flat panel in order to produce to give you better result. And this position is required for the once you want to join the tubular section. You need to offset a bit the tool from the center line. Okay, this is what I get from my previous experiment. So this is before the process, and this is after the joining process. So we can get a very excellent, good surface condition and good joining condition for our specimen for all the parameters that we selected for. Okay, we also managed to use to weld dissimilar plate thickness. So we have 3 mm plate combined with the 6 mm plate. So this is how we do it in our lab. So this is our simple design, simple jig, in order for us to proceed with the process. So for this experiment, we managed to grab a gold medal during our nuclear innovation in Bangi last year. Okay, and this is the template that we proceed. This template is about 1.5 millimeters thick. So we also managed to join this template together perfectly. This is for the joining that we get for this similar thickness. So as you can see on the slide, we have we can get a very good joining process lah, good cross weld section. Okay, for now, we already upgrade our next step. Mission. This is the previous practice. The previous practice will limit us to utilize this process further for the industrial practice in terms of tubular joining section. So in order for us to try to eliminate the inner support, so we have proposed some new setting in order for us to eliminate this internal support. So instead of using the conventional shape of tube, we try to use bobbing tool for our new setup in order for us to eliminate this inner support. And we try on the PVC pipe, and for the first try run, we managed to weld them together perfectly, but not so perfect. But I think we managed to weld it properly for the full wet cycle. So this is our new tool design in order for us to upgrade this conventional milling machine available in our workshop as a new friction stir welding machine. Okay, this is our status of application on site. So currently we use this technology or facility as part of UniKL teaching and learning activities lah for our degree and diploma student, and also for our master and PhD postgraduate. Okay, in terms of yeah.
Good morning, Professor. Actually, I'm just connecting in my laptop now. Just I thought I could come in the what you call I'm just in the cell phone. I'm just trying to connect. If not, I will just try to make a presentation. So I will just
okay, bro. You can proceed after me.
I will just WhatsApp the thing. I'm just connecting it. Another 2 minutes. I will be just because I'm in US now.
We are a bit delayed, bro.
So, huh?
Yeah, we are a bit delayed. We will present after this.
Okay. No problem.
Okay,
then I can get connected. No problem for me.
Yeah.
Thank you very much.
Okay, this is the potential use of friction stir welding process for marine application. As you can see on the slide, we can proceed for the pipeline joining. So this is my expertise, pipeline joining, and we also can utilize this process in order to fabricate bulkhead. So this is the flat panel bulkhead, and also deck panel for the ship, surface ship, and also other part like this is the the position of the deck panel, bulkhead, and also the pipeline in marine application. Okay, this is how we do it for flat panel setup. This is the two workpiece, and we have the backing plate in order for us to make this two join successfully. And also for the T joint, we can utilize this kind of backing block setting in order for us to weld them successfully. And this is a worldwide application. As we can see, Megastir also have their own friction stir pipe welding process at their facility. But as you can see on the slide, their tool is very big and bulky, compared to mine. So this is mine, a very small one. This is I managed to have this setting during my PhD process at UTP, and we also can have like this portable friction stir welding in Cairns, Australia, and also as you can see on your right side, the EU mobile web project with the cost about euro 1.5 million available on their site. Okay, this is a surface ship that was built by using this technology. As you can see, the world contain friction stir welded decks on board. And also we have superliner Ogasawara in Japan, and also the Boss motor yacht using this kind of technology, and also for naval class surface ship Kobe class new generation Steve missile fast attack craft in China. And in Malaysia, we have one company that focusing in friction stir welding in Port Klang. I found only one company that specialized for friction stir welding process locally, but this company was come from UK. So they set up their branch in Port Klang in order to focus on the formwork activities for the building construction. So they will have this aluminum panel constructed by using fully in a friction stir welding process. Okay. So for commercial user, as you can see on slide, we have several players, several users that utilize this kind of technology in their practice. For inspection methods, I think we can proceed with the visual inspection by using the conventional wet gauge. And additionally, we can run for ultrasound phase area inspection. And the latest one, you can go with the computed radiographic testing with these acceptance standards as listed on the slide. We have ABS, we have ISO 25239, and also this AWS, American Welding Society D17.3. Also for the last standard for the last part too, they focus on the tubular section. Okay, as we can conclude, friction stir welding is good alternative welding method for marine application, especially in terms of prefabricated parts. We focus on the uniform parts like say flat panel and also for the tubular section. So that's why you can see we can use it on the deck construction, bulkhead construction, and also for the pipeline joining process. This friction stir welding can be used to cater the similar thickness of metal with proper joining arrangement. If you can have those proper setup, you also can join this similar thickness of metal successfully and perfectly. This could improve the quality of welded parts to directly benefit the end user safety and investment in terms of cost saving. So, as you can see, this process eliminates upraise, eliminates fumes, and also eliminates the use of filler metal. So if we guarantee the operator safety and also the in terms of cost saving practice in the state or in the state organization. Okay, I hope this will further promote friction stir welding for industrial application. So I think I will end my presentation. Before that, I would like to thank all my collaborators during my active research on this tabular section practice. And I think that's all, Doctor. Assalamualaikum. If you have any question, yeah, you may proceed to ask me now. I think.
Okay, thank you, Dr. Azman, for the very good and interesting presentation. I would like to open floor for any question.
Professor,
Any
question. Professor, one question from my side.
Yeah, Prof.
Yeah, Prof.
You are working on the friction stir welding, basically
Yeah.
for the marine application. So, what are the materials you are using?
For now, I'm using 5083 and also 6063.
Okay.
For 5000 series and 6000 series.
Okay.
Yeah.
See, I am also working in the marine applications. So, wherein we do the laser beam welding for nitronic steel, so nitronic 50 steel. So that also have some corrosion resistant property since it has the nitrogen. So I think we could see how in future we could try to collaborate on this project with you.
Yeah, sure, Prof.
I'm looking forward.
I'm looking forward to collaborate
To work on this.
with other expertise.
Okay, thank you, Professor.
Thanks, Prof.
Yeah. Okay, thank you, Prof, for the question. Okay, any question from the floor here? Physical.
Assalamualaikum.
Salam.
Can you hear me? Okay, Dr. Azman, I have one question. As we know that the FSW, most of the experiment or equipment, they are rigid, right?
Yeah.
In the bulky machine. So there is a possibility make it the machine portable. Like the other welding set that you can find at market now. There is a possibility that the FSW can be compact and make it portable.
For me, as you can see, Dr. Azam, I'm focusing on the tubular section, right? So for now, this is my I try to eliminate the internal support in order for me to make it mobilized. That's mean I want to make it portable. That's mean I'm not focusing only on in the laboratory, but also I can bring this tool outside. Because we have like long pipeline, right? So we cannot join them in our lab. So we need to join them on site. So we try to eliminate this one first, and then hopefully in future we could manage make it one portable friction stir welding machine to cater for this pipeline joining. Hopefully.
I see.
But for now, we can see for the positive result hopefully we can cater for the metal parts, but because for now we just try for the softer material, not the metal parts. But for the first step, it will give us a very positive output.
I see. Okay. Thank you.
All right.
Okay, thank you, Dr. Azam, for the question. Any other question from the room, from the seminar room? Okay, I have one question. All right, we know that when we talk about marine application, you are dealing with very large or very big structure. Okay, for a straight, probably for the tubular is not that critical, but for the straight application, I think endurance is one of the very main element to be catered, because when you talk about friction stir, there is a heat involved. When we talk about very long or time consuming or very long structure, which require time and heat definitely will be very high for that application. Do you have any experience on that, on dealing with on how much or how maximum in terms of time the process of FSW can proceed?
Doctor, for the deck panel, I think for 6 meter long, we can successfully manage to weld them together within 5 minutes.
Is there any effect on the tool and else?
The tool, like I said before, we can use one tool for up to 1 kilometer wet length. Then we need to start to change the tool. So it's very cost effective process lah for me. Because with the one single tool, we managed to weld successfully for 1 kilometer wet line before we change to a new one.
Yeah.
But as you can see on the screen, Doctor, we need still to make it have like a combination lah between conventional method and with the friction stir welding.
Yeah.
For the difficult angle, we still require the mix process, additional to friction stir welding.
Yeah.
But for the straight line, we can successfully weld for the 6 meter line within less than 5 minutes with no distortion.
Okay. Any question from Zul? Okay. If there is no more question, thank you again to the Dr. Azman for his interesting and informative presentation. I think because I have a few students as well now struggling for their study to complete their study in FSW. Hopefully they can get something from this presentation. Okay, again, I would like to thank Dr. Azman for the presentation. Okay, we proceed with the second invited speakers from Prof. Rajendran from Automobile Engineering from MFRL, Chennai, India. I know Prof from our collaboration in the one of the matching grant with the sponsors by the one of the university in Taiwan at the time on the tribological performance of the wire arc additive manufacturing at the time. I think one the student already completed. All right, without further delay, I would like to request the Prof. Rajendran to start his presentation. Okay. Prof, please.
Good morning, Professor. Thank you for giving me an opportunity to present my work in this seminar. So my title is Enhancement of Automotive Component by Surface Engineering. So we all know that the wear and corrosion in any component plays a major role. So we have a friction between two components that leads to the wear, and there is a loss. And similarly, because of the corrosion due to the chemical action or any other environmental change, so there is a wear and corrosion, which shows that there is a need for protection of the component. And we also know that the nation's GDP is something throughout the world. It's something like 4 to 5% of the GDP is spent for the repair or the maintenance of the automotive components, or in general the engineering components. So the main reason why we are just trying to do here is to protect the surface by surface engineering. We could also say we are just trying to give a coating on the automotive component, which is also we are trying to add this surface. So it's also, we can say that it's an additive manufacturing process. So the main theme of the seminar, which says that we go with the new trends and technology. We have been talking about the friction stir welding, the metal additive manufacturing. So this is also one case wherein we are just trying to see how we could add a new surface or a new material to the existing one to enhance the properties. So with this introduction, we'll just go into the content. So we all know what is the basic material science. We have the structure, property, processing relation. So this is what, with this, we are just trying to see how we could get the required properties for our automotive component. So we play with the process. So if you need, we have been talking about the FCC structure, then we will be able to get a ductile material. So when we go for the processing, we have different manufacturing process. So we do something like an heat treatment, the carburizing or nitriding. Thereby you improve the fatigue resistance of the automotive component. That is what you are just improving the property. So you can either change the structure or you can change the properties by processing or the manufacturing process. Then you will be able to get the required performance. So this is a basic with which we have been trying to see how we could have the structure property relation with the different manufacturing process. I think this is something, the materials information which is required for the design. So we all look into the characterization in any materials thing. So we try to see how we could do the test and then try to capture the data. And then you have the design data or the information based on which you try to see how you can select the material and the process. And not only the potential thing you need to look into the application, but also you need to see how it should be financially or economically business-wise. So this is how you take up a project or try to see how you can characterize and go in for the selection and implementation of the material or the coating or whatever you are doing. So what are the requirements for the engineering surfaces? So we have been talking about various failures. So you say the corrosion, then you have the friction, which could be a low or high. Then you have got something like a wear. So you have got a fatigue. We have got a rolling and bending fatigue, and also we have the oxidation. So when you talk about the loss of usefulness, you could see the surface degradation, the wear and corrosion plays a major role. So what is that we are just trying to do? So we are trying to see how we could increase the component life, and thereby you try to reduce the maintenance and the replacement cost. So we also try to see how we could avoid the excessive component breakdown, and thereby you try to limit the losses because of the material that has been getting degraded. So you need to see how you need to reduce the investment cost through the increased machinery life. So I'm just trying to take a case study See, I've just, though we have I've done work on the lot of automotive components like a piston rings and the exhaust thing, wherein I'm just trying to focus only on one particular product which I have done for my research. So basically, I've taken the piston ring. So you all know the function of the piston ring. So which will be over the piston and it will be just rubbing over the cylinder liner. So what should be the property is the piston ring should have a sufficient hardness and it should not get what you call be harder than the cylinder liner. So we need to be careful in such a way that the base material what you are using for the process should be have a sufficient hardness. So what is the need for the project is the India Piston Rings, the company which sponsored me for the research, they have been importing martensitic stainless steel from Japan, and then they have been doing the nitriding process, and they wanted to have a replacement for this particular martensitic steel after nitriding. So that's how this project came into picture. So we started working on the low cost material, or we wanted to reduce the cost of the material which has been imported from Japan. So we selected the low cost material, which is basically the steel. So once I think the steel is a one which is a very versatile material wherein you can just play whatever you feel like. So what we did is we have just gone into the aluminizing process. So we had the hot dip aluminizing process wherein we have just got the layer. After aluminizing, we have just tried to diffuse it so that the material is being transferred into the base material, and then followed by the diffusion, we have gone into the gas nitriding process. So the basic idea is why we have gone for the nitriding. So as I have already mentioned in the beginning, so nitriding is the one which gives the fatigue resistance. So we are talking about the fatigue resistance, which means that the material will be subjected to continuous compressive and tensile stress, or the forces will be acting. So you have both positive and the negative forces will be acting on it. So when you talk about the piston ring, we all know that it is subjected to wear, and it is also subjected to the corrosion. So you have got something like an your chemicals that will be getting from the combustion will be getting impacted on the piston ring. So we need to choose a coating in such a way that it has to resist all this property. So we are looking in for the good thermal conductivity, good corrosion resistance, good wear resistance. But in this case, we can say it's a corrosive wear which we are looking in for. So we have just chosen the aluminum because aluminum is the strongest nitrate former out of the various metals. So you've got something like an aluminum, then you've got titanium, then you've got the molybdenum, which forms strong nitriding when you have the reaction with gas nitriding. So you've got, I've just mentioned, so high hardness is achieved by nitriding the alloy steels usually, which contains aluminum, chromium, molybdenum, and vanadium. So these steels are very expensive. So what we are trying to do is we are just trying to see how we could form this hard and stable nitride when the base material comes in contact with the nitrogen alloy. So instead of going in for the special alloy steel, we are just trying to see how we could achieve the same with the low cost material. So I will just give what is the basic concept. So this has been the need for the coating on the piston ring by aluminizing and nitriding based on the requirement of the industry to go in for the low cost material. We have chosen the aluminizing and nitriding process, which led to high hardness and the wear resistance. So why we are going for the nitriding? So it's a case hardening process, which is subjected to 530 to 580 degrees centigrade. So the principal reasons are for nitriding is it has got a good fatigue resistance, increased wear resistance, and improved corrosion resistance. As I have already mentioned, aluminum is the strongest nitride former. So this aluminum containing steel will yield the best nitriding result, when thereby improving the wear and the fatigue resistance. And why we have chosen the aluminizing? So aluminizing, you are just trying to diffuse the aluminum into the base material. The temperature range is 600 to 1000 degrees centigrade. It has got a high temperature oxidation resistance, high corrosion resistance. So this combination will give a better results for the automotive applications. So we have been trying to see how we could improve the properties. So this is the process which has been followed. We have just chosen the medium carbon steel. So I have just given the composition 0.36% of carbon, and we have just gone into the normal surface preparation, which involves the acid cleaning, water rinsing, and drying and shot blasting. Thereby, you'll be able to get a good or a better adhesion property. So we have followed the hot dip aluminizing. The temperature is 715 degrees centigrade. Time, we have just tried to optimize it. The composition of the aluminum silicon alloy is, it's an eutectic alloy. So basically, we have just gone in for the high temperature. Thereby, you try to maintain the fluidity of the bath. Thereby, you can just try to get the required coating. And we have gone into the diffusion treatment to diffuse the aluminum into the metal. And after the diffusion, we have just used the temperature of 600 to 900 degrees centigrade, and with varying time 2 to 8 hours. And followed by that, we have just gone into the gas nitriding. So we will be able to get the required hard nitride layer. And also in this case, when you are going for the gas nitriding, the white layer which is formed during the nitriding is getting reduced. The temperature is very low, 550 degrees centigrade. And we have gone into the different gas nitriding time like 8, 9, and 11 hours. So this talks about the material characterization, which we have already done. So the microstructural analysis to analyze the different layers of the coating. So hardness has been done, X-ray and wear test has been done. I will just go into the actual details. So we have, so when you look into the microstructure, so we have gone with a different thing. See, in some cases we could see there is an thickness is somewhat more, and you got a uniform layer. See, in the first one, when you have a dip time is very less, you could get just a layer which has been formed. Whereas when you have the different time positions and the thing, the layer is more, but it's sometimes broken. So we have just found some what do you call it, when the dip time is something like in 5 minutes, we could see that when the diffusion time is also more, we could get an uniform layer, and the aluminum layers, that gets peeled off automatically when you have with the high temperature, leading to the nice bonding between the base material and the aluminum. So this talks about the micro harness. So we could see that we are being able to achieve an harness of something like an 600 to 700 HV in aluminized and diffused, whereas the base material has got something like 350 HV, the weakest harness. And when you go in for the nitriding, we are able to achieve 1100 HV at 0.1. So which is equivalent to the value what the company is getting with the current steel, the mortar steel with nitriding. They are able to get the same thing we are being able to get with the low cost material. So this talks about the how the material has been diffused and then nitrided. So this gives the structure how the nitriding layer has been formed. You could see 2 layers in each picture. So you have got the original layer and the nitriding, the original layer and the nitriding, and then the original layer and the top of it, you are able to get the nitriding, which gives the harness value. So in case of the aluminized and diffused, we are being able to get something more. In this case, you could see something like 900 and 950, depending on the which dip time you have been using. So what is the conclusion we've got is when you are just trying to have the process parameter optimized, we have been trying to have that one. So we have been able to see how that could be understood in a better way when we have the microstructure as well as the what you call the micro harness graphs. So from that you could see the values, and then we have been able to get the harness value. So this you could see something like an 1200 or 900. So which means that when you are just trying to increase the dip time to 5 minutes, and when you have something like an diffusion time with more than what you call it, the temperature with 900 degrees centigrade, and the diffusion time with 8 hours, and we have been able to get good results. So, and also we have been able to look into the XRD of the aluminized and diffused samples, wherein we could see the aluminum nitride layer. So you could see the peaks here 33.4 and 35.7, and we have been able to see that we have got the required material what we have been able to achieve, which has been confirmed from the XRD. And we have also done some wear testing, wherein we could see the wear rate is drastically reduced. So you could see the material has got a good improvement. See, and also we have just done some friction. So that is also have got a very low value. So finally, to conclude, we can say the higher diffusion temperature yielded some porous, but and the low temperature dip time has got a thin layer of case depth. So when you just consider the diffusion layer thickness, see, one of the main requirement in the piston ring application is we need to look into the dimensional stability. So you can't increase the dimension or the thickness of the coating, because when you have a more coating, then that may damage the or it may not fit into the piston cylinder bore, and that may damage the cylinder liner. So we also need to consider the diffusion layer thickness. So based on that, we have got some parameters, and we have been able to achieve the good results. So using the surface engineering process by combination of two methods, the surface engineering, the aluminizing and nitriding, we have been able to get good results with the piston ring. So this is the one project we have done, and there are more problems wherein we have done for the exhaust application, wherein we have been trying to choose electroless nickel coating also for improving the process. So we have done chrome plating, then you have done with the nickel plating, and then we have done with the aluminizing, and we have got a good results, and we have done comparative studies. And apart from that, we have also done studies on the piston, wherein we have been trying to see how we could the thermal properties could be improved on the piston top, thereby it could resist the heat resistance. So I have just because of the time constraint, we have just taken one case study and then found how the process or the automotive component properties could be enhanced by the surface engineering, which we can say it's an additive process or the additive manufacturing, wherein we are just trying to add the material to the product or the component. So with this, I just conclude my talk. So I think if you have any queries or anything, you can feel free to ask, or you can just have a discussion on that. So this is basically for the piston ring. So I'd like to thank the IP Rings Limited, India Pistons, for the support in this project. So thank you for the opportunity, Professor.
Okay, thank you for the interesting presentation. Is there any questions from the floor? Okay, actually I have one question.
Yeah,
I try to relate to the processes that or to the research that we are doing now. For example, in friction stir welding, when we are dealing with two different type of materials. For example, we join aluminum with. Can you hear me, Prof? Okay.
Yeah.
Okay. We try to join between aluminum and steel. My steel. Okay, we know that not all material can be heat treated. In this case, for example, we know that from the friction stir welding, the material already been mixed between those materials. So most like the properties of the joint area already being changed because of that mixture. We know that from the heat treatment process itself, we need to set for optimal process, optimal parameters. In this case, Prof, how we can deal with it, because we are dealing with two type of material, and there are two different set of process parameter for the heat treatment.
Yeah, see, the question what you are asking is generally when you have the friction stir welding, so when you join two different materials, so we need to look in for the how the material is being getting affected. So when you talk about the aluminum, the melting point is something like 690 degrees centigrade. It depends on the what is the alloy, but what is the heat treatment we are talking about is something you'll be having at the annealing process, or what type of process, because one is a ferrous and another is a non-ferrous. So there may be a changes in that we need to look into that case by case and then do. So mostly the process, sometimes we'll be doing it with less temperature, something like 500 degrees centigrade. That depends on whether we are trying to relieve the stress or whether we wanted to improve the properties. So that depends on that. So we need to have a optimize of the temperature also, as you suggested, so that we need to have a detailed one, because it's a one is the ferrous and another is non-ferrous. One is a low temperature, one is a high temperature. We need to see what is the property we are looking in for, what is the purpose of the heat treatment we wanted to do. So based on that, we need to select the required heat treatment process for that.
Yeah.
Hope I have cleared it.
Yeah. Okay, Prof, I got it because from our experience, we have tested. One of my students already tested because we know that, for example, my steel is consider my steel as a non-heat treatable. But in this case, when we have studied on the formability of the material, most likely when we heat treated, there is effect on the performance of the in this case the wind bending process. That's why we asking you on this case. Hopefully we can apply and implement in our research in the future. All right, Prof. Thank you. Any other question? Any other questions from the floor? Yeah, Zul, related to your project.
So even if in future you can just try to get in touch, and then we will be able to answer it. Actually, thank you for the opportunity. Actually, I have just been looking into the WhatsApp. That's how I just got connected. I thought it's on 27th. Fortunately, I was awake. I was about to go to bed. Now the time is 10 o'clock.
Yeah.
Thank you, Professor, for your.
Thank you, Prof, again for sharing your thought about the subject. We are very honored to have you in the presentation. Thank you again, Prof.
Sure. Next time we will try to see whether I could come in person and then make the presentation. That would be fine.
All right.
Thank you for the opportunity.
Thank you, Prof. Thank you again for the presentation. All right.
Okay, thank you.
Okay, thank you.
I will just leave because I need to. It's already 10 now.
Okay, thank you, Prof.
Yeah.
Okay. Yeah, it's already 10. I think we will proceed with the next presenter, which is Fadil. I think Fadil also have a very tight schedule today. So hopefully time at 10 a.m. is just on time for his turn to present his presentation. All right, Fadil, you can proceed.
Okay, hold on. Just get things ready. Okay. Oh, still getting things right. Okay, let me share my screen. Yeah, can you see my screen? Yeah. Okay. Good morning, everybody. Today I'll be presenting on the work on the formability analysis of aluminum telephotic blanks welded by low-powered laser for lightweight automotive application. Okay, this is a project with Prof. Baha, the Zahurin and Professor Associate Prof. Razila from UM. Okay, I think this is a site that many of us witnessed over the holiday, where we are going back for Hari Raya, and there are lots of cars on the road, and the amount of cars and automobile will be increasing. It's not decreasing; it's always be increasing, and this is a problem with environmental problems lah, and with all the carbon dioxide emission and greenhouse gases. So governments have been implementing or discussing on how to reduce the amount of emission from vehicle. And one of the methods is to propose lightweighting strategies. So the outline of my presentation is presented here, normal problem statement, methods, and results in discussion and conclusion. So coming back to the idea of lightweighting, this is on how to reduce the weights of vehicle by focusing on 3 strategies, on material, on component design, and also in production processes. So one of the design component is called a tailored welded blanks, whereby you are making components with different thickness or different alloy composition, which is welded and then form into the required components, so that the components will be lighter without sacrificing the performance, meaning that the strength and requirements, the mechanical and requirements, it is still being maintained. So this is an example of tailor-welded components of an automobile, which is a car door component. Okay, and in coming back to the idea of lightweighting, there has been maybe interest in the use of aluminium for automotive production. And in terms of advantages, meaning that it can, because it's lighter, it can save fuel, increase power handling performance, and also in terms of environmental performance. But it comes at the disadvantage of it's higher cost than steel. And because aluminum is not so familiar, it can be more complex to produce, and it is more challenging to weld and repair. So in this study, this is a long study, we one component that we are looking at is the characterization of post-weld formability, meaning that it is being used research is being done for welding, but in terms of post-weld characteristic, especially formability, it is not yet to be fully explored. So coming back to the formability analysis, from past studies, it was seen that in terms of formability of welded blanks, that there is a significant reduction in formability where the failure is occurring at the thinner region. And then mostly the literature have shown that even though sometimes when we do the initial mechanical test, it shows a good result, but when we do formability analysis, the result is not so very good, as shown by Ahmad et al. So in this presentation, we want to see the formability of aluminium tailor-welded blanks of selected low power laser welded alloy specimens. So as you can shown here, that we are welding two components, specimen A and B. Can be one type of alloy, and B can be another type of alloy, or A can be one type of the same type of alloy but of different thicknesses. So from preliminary tests, we have found that using low power laser welding, it cannot weld in one pass. So what we have done is that we weld it in two passes, meaning weld on one side and we're turning it over and then welding it on the second pass. And this is the machine that we have used. And for our test studies, we are selecting the element alloy 5 series and element alloy 6 series. And for the formability test, we have used a limiting dome height test, which is apparatus, which was fabricated in-house following certain guidelines, certain standards. And then what we are testing here is we want to test the punch. You have the punch here. We want to see how the specimen will be affected by the punch, and then we want to see how high that the punch can create the dome of the specimen. So if you can see here, the gray is the specimen clamped in between the top plate and the mid plate, and we mounted this setup in an Instron UTM, and we secured the plates, the specimen, and using a torque wrench, we can secure the specimen in place. Specimen that I have chosen is there's 3 groups. The similar specimens, similar alloy pair, but with different thickness, 1.5 and 1 mm. And then we have different alloys and different with a similar thickness, and also this similar thickness, 1.0, 1.5. And this is the results of the test. As you can, this is for a the base specimen, meaning that base specimen, you can see that the punch has created the height, the dome height, and the fracture is seen around the dome. For the base metal, we can see that the crack occurs in the vicinity of the dome. So from the results of the test for the base material, you can see that it goes for the 5 series and the 6 series. The height reaches to from 11 mm to around 13 mm based on the thickness. And you can see that you can see a clear onset of failure. But for the welded specimen, if you can see from the top left corner, the onset of failure is not so clear. So we need to observe the graph of the tensile from the tensile machine, and we can observe where does the drop occurs. So we can see that we can check from the graph where does the crack occurs. And from the results, we can see we have conducted for the 2 groups, Group A, Group B, and Group C. And in general, it goes from 3 mm to 5.62 mm. So it is much less than the parent materials. some observation that was seen is that a higher dome height is achieved for higher welding speed. If you can see from the graph on the left, meaning that from in general for higher welding speed and higher laser power, a higher dome height tends to be achieved, and for lower laser, smallest dome height was obtained for the lowest laser power of 270 watt, which we think is indicate of insufficient heat input into well. And there was no apparent influence of varying thickness, because from here you can see 1 and 1.5 more or less it has the same distribution. And if we can combine tabulate the graph the results, we can see there are two defined groups. One to showing the subpar well. Subpar well meaning that the LDH dome height is less than 3.8 mm, and another groups of showing LDH of more than 4, which we assume as a good indication of a superior well quality. And so we can say that increasing the laser power can reduce the number of substandard welded specimen. So when we do the formability test, then only we can see that some of the well, even though in the tensile test they're showing some good result, but actually it is not so good quality if you put it in the forming test. And in terms of failure location, as this similar to what have been reported in literature, the failure will tend to occur at the thinner section of the well. But for specimen with the same thickness, the site is inconsistent. But it will occur at the weld line, but it is slightly offset. It's not directly on the weld line, but it is slightly either to the left or to the right. And if we from our previous test on we are not showing here micro hardness, there are some softening zones beyond right next to the weld fusion zone. So in general, the quality of the weld specimen falls within 4.5 to 5.6 mm, which is a reduction of around 50 to 62% as compared to the values for the base material. So this results is comparable to those made by other researchers. For Basil et al., 2002, they have reported a 47% decrease in punch displacement, and another report reported an 88% decrease in punch displacement. So it is expected result that is comparable to other researchers. And as I said before, the fracture will consistently take place along the weld line, and which is pertains to the region of reduced hardness. So I've not shown the micro hardness test here, but we have seen that this is lower on the beside the fusion zone. So in conclusion, we can see that the specimen fracture for welded test will always occur along the weld line, and increasing the laser power tends to decrease the number of subpar welded specimens. And in our case, for the dome heights, which was approximately 52 to 60% of the dome height achieved by the base metal alloys. With that, I will conclude my presentation for this session, and I will open the floor for any question. Thank you very much.
Yeah, okay. Thank you for the interesting presentation. All right, I would like to open to the floor for any question. Jadi Adil is preparing his slide as well for the Bawah Bosi that inshallah will be in June. Like that.
InsyaAllah.
Okay, and any question from the floor? Yeah, Azul. Dekat try, dengar. Dengar, can you hear Adil?
It's not so clear.
Yeah.
Hello.
Hello. Ah.
I have three questions about probability test. The first one is from your experience when doing the probability test. When is the how to know the exact moment when sample break so that you can stop the test. So and then because I also doing probability and my picture the G is a closed system. So I want able to know what happened there. Sometimes is already formed until withdrawn. So the sample is not valid anymore. So this for the first question. The second question is some probability LDH test use grid edge onto the surface. So compared to the taking the height until failure. So what's the difference between these two methods? Also, for the third question, let's say the failure, the crack happens at the well. Is the sample still valid for consider as a result? It's a valid result. Okay, thank you.
Okay, thank you, Azul.
Okay, I more or less hear the question, but maybe the third question I need to repeat. So correct me. The first question is that we can how do we identify the point of failure, right? During the test, meaning that it's when you take out it's already formed. So this is what I already experienced also, meaning that where do we identify the point of failure? So what some of the specimen that I tested, some of them we cannot actually identify the drop. So it is very difficult to identify without recording the load. So in my case, I mounted it in the instrument. So memang after sometimes you cannot see the drop of the load. When you take the specimen out, it's already formed. But for example, I did some preliminary, so I know that the failure will occur at maximum 6 mm. So what I did is that I tested it, and then if I cannot detect the failure while experimenting, I will leave it until it reaches 6 or 7 mm, and I will take out, and the data I will, analyze balik lah that data tu, and then we use the you can use the some of the Excel ataupun or the graphing software to draw the graph and to zoom in where you can actually more or less detect the load, the drop in load. That you can, but some of the specimen you cannot detect lah. Sometimes it fails early, and in my case, maybe one few will be rejected. Okay, so nak tak nak we have to use some sort of load cell ataupun sort of data acquisition to detect to read to take the results and analyze later on. On the second question on the grid circle, the grid circle, I also did the grid circle, but I'm not presented here. the grid circle analysis GRA, it is used for determining the limits of forming, which is a bit difficult to do, but because of in terms of how to read the grid lah. But it is another indication of formability, and from that GCA you can actually draw the limits of where can the safe limits of the forming, and whether if you exceed it, you will fail. So if you do enough specimen, you can actually plot the results. And in my case, I did some preliminary also in of the circle analysis, and we can actually suggest regions of where you can where is the performance of the welded as compared to the of the parameter. It's just another indication of formability lah. And the third question, I couldn't hear it. If you can repeat it.
Still very
Yeah, if the well happen or occur at the well line, is it still reliable or can be accepted as a result?
The failure occur at the well line.
Yeah.
The failure occur at the well line. Yes, in my case, it's still okay, because it will fail at the well line. That's the region of the weakest point lah. Kalau weakest, dia akan fall kat situ lah. Fail along the well line. Kalau if what I seen was that for some of the base material, it will occur at around the center, but for the welded specimen, what was seen was that it will occur along the well line, which I think was because of the that is the weakest point, and that was also reported by some other past researchers also.
Okay. Any other question? Okay, I have one question. Your title is about low power laser, right?
Yes.
What are the advantages of low power laser compared than other type of high power or common type of laser being used in industry?
Okay. Low power laser is, for example, the heat input is lower. The heat input is lower. But I think high power also we can actually control the heat input by using pulse or using very short duration. But a low power laser for continuous well, one is that the apparatus is much more less expensive than the high power laser. In terms of maintenance, is much easier. The apparatus is much simpler. And then in terms of more or less, that's the one of the main reason in terms of procurement. In terms of, for example, in production, then the cost outcome is much lesser than high powered laser. Yeah.
Okay. Did you consider any cost analysis in your study?
I didn't do the cost analysis in my study, but there are some reports of comparing the power of laser with those of other fusion processes.
All right. Okay. Thank you, Fadil, for the presentation.
Thank you.
Thank you for your time as well. Thank you for the questions. All right. Actually, we do have we skip two presenters because Kamaro is not able to present or to join our presentation today. Same to Hakim. So we proceed with the Office Ame for his presentation. Ame is already in his third year of PhD in the finalizing his experiment. Hopefully, he managed to end before he go back to his workplace. All right, Ame, please. Cut dulu. Ni.
Okay. Yeah, thank you. Bahar. Testing. Okay. Okay, thank you, MC, Dr. Bahar. Assalamualaikum and very good morning to all the participants and the audience online and offline. Okay, my name is Amir Safi MC, student, postgrad student, the Dr. Bahar School of Mechanical Formula Research Lab. So today I would like to share my research about friction stir welding process. So my research is focusing on how to strengthen the joint produced by friction stir welding in thin sheet metals. So for my study, the thin sheet metal is focusing on the aluminiums. So my topic today is Taguchi-based optimizations of friction stir welding machining, parameters of this medium thickness, thin sheet aluminum 6061 T6 in double butt lap joint configurations. Okay, as we know that friction stir welding is a solid state welding process that has gained significant attention in the manufacturing industry due to its numerous advantages over traditional welding methods. So I think before this, the government has explained detailing about the friction stir welding, the advantages and also disadvantages the friction stir welding. So telluride blank produced by the friction stir welding technique has various advantages of a typical welding method such as IG and MIG, including the ability to better preserve sheet formability and improve structural strength. So my focus on the joint configuration, which can call it as a double butt leg joint. So double butt leg joint is a modification on the square butt joint configurations, which is used to improve the welding contact area by staging two touching surface of two blanks. So as you can see at the figure 1, it shows that the difference between the double butt leg joint and other joint configuration during the friction stir welding process. So at the figure 1, you can see at the top is called a scuff joint. So this joint has like an angle plate at the edge. So the welding will be occurs in over the area. At the middle is we call it as a square bar. So this is the common welding joint configuration used in the conventional welding or in friction stir welding. And the last one at the bottom is the double butt leg joint. So this is what I am focusing in my study, which is to increase the joint quality of the friction stir welding. So this research aims to contribute to the advancement of the friction stir welding technique for thin sheet metal, particularly in the context of the similar thickness joint, and offerings valuable insight for industrial application. So the objective of my study is to investigate the optimal parameter of friction stir welding in a double butt lap joint configuration for the similar thickness aluminum 6061 and the effects on mechanical properties. Okay, we move to the literature review. So the investigation into the friction stir welding joint configuration is experiencing rapid movement and advancement with the introduction and the study of various alternative joint aimed at enhancing welding strength. Certain joint shapes such as scuff joint, stagger joint, and double butt joint have demonstrated superior results compared to the traditional joint. So the double butt joint can be further explored and applied to various engineering fields, considering its utility in joining material of uniform varying thickness. Previous study found that double butt joint is 6 to 11% higher compared to other joints in terms of UTS and the weaker hardness. So double butt joint were also found to be higher than those of the square butt joint configurations. Okay, we continue about the friction stir welding parameter. So here I list all the parameters involved in friction stir welding. There are a lot of parameters involved, so to make it simple and easy to understand, I have divided into two sections, which is under machine and the material. So under machine, we can see the parameter that involved is tool design, welding parameter, axial force, and machine types. And for under the material parameter, you see there are four main parameter, which is thickness, type of material, joint configuration, and the fixtures. So under tool design, I have expand it to three parameter, which is shoulder design, pin design, and tool material. Under welding parameter, we have spindle rotation, fit rate, plunge rate, and tool offset. Under axial force, we have plunge depth and tip angle. And under machine, we have three machine dedicated friction stir welding machine, a vertical milling machine, and the CNC milling machine. And under the thickness, we have same thickness and different thicknesses. And type of material, we have similar material, dissimilar material, the position of advanced side and rotating side, and the rolling directions. Under the joint configuration, we have butt joint, lap joint, T-joint, and alternative joint. And under fixtures, we have fixed or the flexible fixtures. So the selection of the main parameter to be studied has been done by many researchers. So Jeet et al. Identified several process parameters for friction stir welding, including tool geometry, material of the tool and the workpiece, rotational speed of the tool, and the traverse speed. Smera et al. Conduct successful friction stir welding using different welding parameter and found that rotational speed and traverse speed were significant. And the last one is Uvaresh highlight that among factor influencing friction stir welding, welded dissimilar joint, the angle was the most influential. So that's referring to the majority of the researchers, and by doing a lot of literature review, I've selected 3 main parameters to be studied, to be optimized in my study, which is a spindle rotation, a feed rate, and the feed angle. So this is the implementation in my study for this optimization. So I have divided it into 3 phases. For the first phase is doing the Taguchi. So to design the experiment using Taguchi method with the help of the Minitab software. So before run the friction stir welding process, the material preparation is also done, where I need to prepare it to cut it to the size of the fixtures, and also to fabricate the double butt joint configuration at the edge of the sheet metal. So the friction stir welding process is done using conventional milling machine. So before running the machine or running the friction stir welding process, several setup need to be done. For example, the tip angle of the spindle's head need to be adjusted manually. Also, the feed rate and the spindle speed need to be set to the required speed or level before running the friction stir welding process. So the second phase is the testing, which the output of the study is to find the hardness and the tensile, which is the ultimate tensile strength. And the last in the phase 2 is to find the optimized parameter. And the last one is phase 3 is to do the confirmation test to validate the result during the optimization process. So we move to the methodology. So if you can see, table 1 show the main parameter and their 3 level. This value used as the base or the main reference, a value to use in Taguchi method to design number of experiments and their parameter combinations. So you can see the table 2 is the result from the using the Taguchi design of experiment, where the total number of experiment is 9 experiment with different value of the parameter. So you can see the 9 experiment have a different 9 combination of the experiment. So after the machining, there are samples to be prepared, which is for the hardness test and the tensile test. So figure 2 show that the size of the teleweather blank 200 times 90, and the specimen orientation for the tensile test and the hardness test. So the specimen for the tensile and hardness is cut using EDM wire cut according to the ASTM E8. So figure 2 show the location of indentations, which is located at the center along the weld region. And figure 3 is the dimension of tensile specimen that will be used for tensile test to get the UTS value. So after the testing, we have the results here, the result of the different numbers of experiment and different combination of parameter. So you can see here the maximum result for hardness is fall under experiment number 5. Also for the maximum UTS result, if the experiments number 5, and the lowest result for the hardness fall under the lowest result for hardness, sorry, it's under experiment number 7, and the lowest result for the UTS is under experiment number 1. Okay, we go to the result effect on the hardness value. So figure 5 show that the result after the Taguchi analysis. The signal to noise ratio for this analysis used as the indicator. So the indicator is the larger is better. So from the graph, it showed that the signals to noise ratio for all 3 parameters, the selection of the optimized parameter is based on the higher value of the SN ratio. So by referring to the graph, we can conclude that the optimal result of the spindle speed is come from the level 2, 865, and for the welding speed, also level 2, 90 mm per minute, and for the tilt angle is level 2, 2 degree. So it can refer, if we refer to the table 4, it shows that the exact value of SN ratio and the rank of each experiment. So the higher SN ratio will be the first rank, which is fall to spindle speed, followed by welding speed and the tilt angles. So this range show that the parameter that influence the most result of the hardness. So according to the rank, we know that the spindle speed is the most dominant parameter that will affect the result of the hardness, and followed by other parameters. So from the result, we know that the optimized parameter for spindle speed is x65, welding speed is 90, and the last one, tilt angle, is 2 degree, all fall in level 2. So the effects, the result effect on the UTS value. So signal to noise ratio, same as before, we choose the larger is better. So we can see the optimized parameter for spindle speed, it fall to level 2, x65, welding speed 90, and the tilt angle is 3. So we can move to the response table for signal noise ratio. We can see the rank. The rank is, first is the welding speed, second is spindle speed, and the last one is the angle. So the optimized parameter, we can conclude that the spindle speed is level 2, welding speed level 2, and the tilt angle is level 3. Sorry, it's a mistake. Okay, we move to another result. So after using the Taguchi analysis, we move to ANOVA. So the purpose we use ANOVA is to help identify which process parameter significantly influence the response variables. So the variable here is the tensile strength and hardness. So by analyzing the variance between the different parameter settings, ANOVA can determine which parameter can contribute most to the output response. So it allows researchers allow us to focus on the critical parameter to be optimized. So for the hardness, the spindle speed has a significant influence on the hardness value with the higher percentage of 66.5%. followed by welding speed and tip angle. And by the calculations using Minitab, the p-value, which is 0.038 less than 0.05, adds more evidence that spindle speed greatly affect the value of hardness. So at the tensile, we see the most percentage that can affect the UTS result is fall under welding speed, which is 63.6%. So welding speed stand out as the most influential factor affecting UTS. It contributes significantly, accounting for 63.6% of the variability. In comparison, other parameters such as welding angle, 21.8%, and the angle, 2.1% have less impact. So the p-value compute for the welding speed parameter is 0.0048, which is below than 0.05 threshold. So this statistic result emphasize the substantial significance of welding speed in determining the variability of the UTS value. So after getting all the optimum value, the parameter, the confirmation test is done. Confirmation test is important step in research to validate the result of the parameter optimization. So the confirmation test for this experiment is done by remachining of the friction stir welding process using the optimal parameter obtained from the result of Taguchi and ANOVA. So the result from both prediction and experiment are compared to analyze whether they have big difference or not. The prediction result for this experiment are obtained using mathematical formula. So you can use another method also to get the prediction result by using software like Minitab. For me, I'm using the mathematical formula prediction by formula mathematics. So as you can see, I selected from Dr. Azam et al. 2019, use mathematical formula to determine the prediction value. So if we can see the result from hardness by using the mathematical formula, the predicted value is 75.3, and by the experiment 73.6. So the error is small, about 2.6%. For UTS, from the mathematical calculation, the predict value is 182.82 megapascal, and the actual is 176.478, which is the difference is also small, 3.5%. So here come the conclusion. So the Taguchi technique was employed to analyze 3 different parameters. As a result of this analysis, several conclusions can be derived. So for achieving optimal hardness value within the stir zone, it is recommended to use a spindle speed of 865 RPM, a welding speed of 90 mm per minute, and the angle of 2 degrees. So by using this parameter, the hardness of the joint can be maximized. So the analysis of variance show that the spindle speed has the highest impact on the variation in hardness value within the stir zone, explaining 66.5 of the total observed variation. Following this, welding speed also notable affect the hardness value, accounting for 9.4% of the variation, and the angle contribute to 7%. And second, to achieve the highest UTS value, it is recommended to use the parameter determined as optimal through Taguchi analysis. So this parameter consists of setting the spindle speed at 856 RPM, welding speed 90 mm per minute, and tip angle to 3 degrees. So the result of the analysis of variance further indicate that the welding speed parameter has the most significant influence on the UTS value, accounting for 63.6%. So in comparison, spindle speed contribute with a significant of 21.8%, while the tip angle has a minimal impact, only 2.1%. So moreover, we compute the p-value below than 0.05 associated with welding speed. It is statistical significant underscore its substantial effect on the ultimate tensile strength. So for the future works, the finding for the Taguchi method analysis provide valuable insight for the optimization of the friction stability process parameter to enhance the mechanical properties of double butt joint. So this insight can be utilized to improve manufacturing process and ultimately contribute to the production of higher quality joint with a superior mechanical performance. So as you can see, there are about 50 type of automotive frame parts, the figure at the sides, left side. So I think that double butt joint configuration can be applied in some of the 50 part, I think. So this double tap joint configuration study need to be extensively explored in the automotive industry. I think for the crashworthiness, since the friction stir welding process nowadays has been widely applied to the car structures. Thank you, I think, for my presentation. So I open for the question.
Yeah. Thank you, Amin, for the presentation. I would like to open question and answer from the seminar room in FLS, the online attendee. Any question? Okay, I have one question. Okay, you have presented two output, try to optimize two output, which is the harness and UTS. Okay, in many applications, we need both properties. We need to have a higher harness as well as higher UTS. How we can compromise by combining both in order to how we can compromise that so that we can get both benefit, not just one.
Okay, thank you. Good question, but I think difficult to answer. Okay, actually for the Taguchi method, we can only select one output, only whether you want to harness or you want to get the UTS. So if you want both, it's quite difficult, but we need to see the applications where you want to apply the friction stability process. So if you want to apply it in the, let's say, a structure like U-shaped structure, maybe it's important you must to see the UTS value, because the structure involved like we apply it to the craftworthiness. Maybe it's important to see whether the importance of the quality of the joint. So the quality is always involved in the tensile. So I think the first you need to prioritize is the UTS, the tensile, and then the second is the harness value. So the prioritize is always UTS. So that's my answer.
Okay, any other question from from the online or from the floor, the seminar room?
I have one question. For the double butt joint,
Yeah, yeah.
how do you prepare the surface? I mean the surface that made for the bed.
The profile, the double
Yeah,
butt. Okay. Okay, thank you, Mr. Zul. So to prepare the double butted joint, so for me right now I'm using CNC milling machines. So but the process you need to use a small size of hand mill. So if you use more than 6 mm diameter hand mill, so it is difficult to fabricate because the thickness of my specimen or my material is only 2 mm and 1.5 mm. So it's very difficult to control. Actually, the depth when we want to remove 0.5 mm, so it's very difficult to remove. So it's easy to use CNC milling, so you can control the depth of cut easily. As compare you fabricate it by using the conventional milling machine. So I do it by using CNC milling machine. Thank you.
Okay, thank you, Amin, for the presentation. I think that's the end of the presentation. So next is we would like to welcome Zul to present his presentation. Baik, saya letak ni. Dia tak hilang dia punya ni. Dia dah stop sharing. Hah? Dia display setting ni dia kena display setting. Keep changes. Nampak? Boleh?
Good morning, everyone. My name is Sukairi. and I'm going to present my work on effect of possible heat treatment on the spring back of the similar friction stir welded plank. So in this study, there were blend of aluminum alloy 6061 and SAE 1020 mild steel was used. And joining these two materials like aluminum and steel is impossible using traditional welding method due to its difference in properties. And this where friction stir welding came in handy, as since it's a solid state process and it doesn't melt the materials and provide a great solution to join similar materials. So the way friction stir welding works is the rotating tool is plunged in between the two materials to be joined, and when the rotating tool is in contact with the materials, friction and heat is generated, which soften both material, and the rotating tool stir and mix both material. As the tool move from one end to another, where line is formed along the path. So it's a pretty simple concept by applying friction and heat to weld two materials. Screwmat is a common defect in sheet metal forming, and it happens as the material tries to return to its original shape after it's being bent or formed. There are many factors affecting the magnitude of spring back in the end product, but the spring back itself is caused by the material properties, mainly the modulus of elasticity, which is an object resistant to being formed plastically. Spring back cannot be eliminated, but it can be compensated and minimized. And what the method to minimize spring back is post-weld heat treatment. And the purpose of BWHT is to reduce the residual stress in weld joint and enhance its resistance to brittle fracture. Since aluminum alloy 6061 is heat treatable while the mild steel is not, so for PWHT of the level blank will be done was done by following temperature requirement for aluminum alloy 6061. For the heat treatment process, as can be seen in the figure, the sample went through solution heat treatment, and then they were heated to annealing temperature of 130 degrees Celsius. And after this temperature has been reached, the samples were held at that temperature for 1 hour. This is a process called battery. This is a process called soaking. Battery nak habis. Hello. This is hello. Dengar? Hello, hello. Hello, hello, hello. Hello. Huh? Dengar tak? After that, the sample will quench in water for rapid cooling until it reach room temperature, and then they will heat once again at a much lower temperature of 200 degrees Celsius for 2 to 6 hours, and this process is called precipitation hardening or artificial aging. and then the sample was soaked in that temperature for 2 to 6 hours before it cooled to room temperature. One of the tests, hello, one one of the tests that can be used to study spring back is by using V-bending test, and for that there are 2 stages of test that has been done. The first stage was to identify the best PWHT artificial aging time from 2 to 6 hours in terms of minimizing the spring back. For the second stage, using the optimum artificial aging time, 2 types of tests were done. Punch stroke is the downward or vertical displacement of puncture from the point of contact with the sample. Another one is the puncture offset test. So instead of placing the puncture right at the well line, the puncture is offset towards either aluminium or steel. Finite element analysis was done for the V-bending test. Modeling was done using SolidWorks, while the simulation was run in ANSYS. There is clearance of 0.05 mm between puncture and plate to avoid localized compression. The 2 planes, although separated, is combined as one part so that it will be a confirmed image. Stiffness behavior for die plane holders and puncture classified as rigid as they are not the focus of simulation, while the plates are classified as flexible. Contact between die and plane holder with the plate established as frictionless. Contact between puncture and plate is defined as frictional with friction coefficient 0.1 and symmetric behavior. And when defining the material properties, the stress strain curve from experimental tensile data were used to achieve simulation and experimental result similarity. For experimental spring back measurement, usually the back angle after unload can be measured using profile projector. However, as the elevated bank is made up of 2 different materials, there is a need to measure the angle separately for both sides of aluminum and steel for a more accurate spring back representation. So the following measurement method was applied. Seeing all those lines there, the idea is to get an accurate center line separating both sides of material, since the weld interface has been distorted by the two stirring action during shutter welding. And by defining the center line, the angle for aluminum and steel side can be measured with the help of digital microscope and image software. The ANSYS simulation result can give the spring back angle by calculating the difference between plate displacement during and after bending. But to measure the spring back angle separately for aluminum and steel side, the result was exported to SolidWorks, and similar to experimental spring back measurement, after the center line has been defined, the angle for both sides can be measured. From the figure here, we can see that one side of the plate has higher angle than the other, which shows the effect of different material properties on its behavior. This is the first stage of V-bending. where different artificial aging time were tested. As can be seen from the graph, the spring back to a sharp increase when PWHT is applied for 2 hours and continue its gradual decrease until 6 hours. So for Telewell blank of alloy 6061 and SAE 1020 MyScale, the spring back decrease as artificial aging time increases. PWHT cause the residual stress to decrease, which leads to decrease in yield strength and eventually the spring back. And similar observation was mentioned by previous work when using the same artificial aging temperature of 200 degrees. However, when using temperature lower than 200 degrees, like 120 or 160, it gave an opposite effect as spring back increase with time. So apart from duration, the artificial aging temperature is crucial for spring back as well. Moving on to the second stage of wave bending test, different punch stroke were tested ranging from 4 to 8 millimeter. And as can be seen from the graph, higher punch stroke leads to lower spring bend. And this pattern is similar for both sample with or without PWHT. As punch stroke increases, the puncture bend the sample even more, which increase the residual stress. And this higher stress turns the material into plastic state, which results in less straining after punch load is removed. And with enough permanent deformation, this will reduce plastic deformation for spring back to happen. For puncture offset test, spring back has different effect depending on which side of puncture the puncture was offset to. And when puncture move away from wear line towards aluminium, the spring back increase. Whereas when puncture move towards mild steel, the spring back decreases. As the point of bend moved further away from wear line, the spring back became less affected by the weld joint mixed material properties and behave more according to the base material. So to recap the finding of this work, artificial aging temperature 200 degrees Celsius and time of 6 hours produce the lowest spring back. Spring back is inversely proportional to punch stroke. Spring back increased as puncture was offset towards aluminium 6061 and decreases when offset towards SAE 1020 mild steel. Sample that went through PWHT produced lower spring back. And finally, experimental result falls within 10% average error compared to the finite element lensing result. Thank you.
Yeah. Okay, thank you, Zul, for the presentation. Okay, I would like to open Q&A to our audience in the seminar room as well as online. Okay, any question? Academy, we have the academy, we have the Hafiz there. Yeah, the Hafiz.
Right. So sample that went through PWHT produce a lower spring back.
Yeah.
Okay. Do you have any estimations regarding on the material side? Do you have done any like XRD regarding on the compound that produced? So you doing the welding process or something like that? Do you have any study on that?
I will. For SRD, yes, I haven't done yet, but I'm planning to do it because I want to see from the two-story reaction, whether they are maybe aluminium particle that went to the steel side and vice versa. So that will explain why even though my steel is a non-degradable material, it's still affected by the heat treatment. Yes, so that's in my plan as well for doing SRD.
Expect have any compound produced?
Sorry?
I mean, or if the test positive have some expectations, right? So that possible to observe the compound and expect any compound form. The
Compound form,
conditions in school.
during the fixture wedding, the tool has softened and mixed these two material for in the inside the well line. So the well lines actually consist of both material opposites.
Compound, right?
Yes.
Compound form.
Yes, yes.
Right.
Thank you, Dr. Hafiz. Any other questions? Before from the online? Yeah, I mean, what?
Oh, okay.
What is the most challenging thing you face during welding aluminum and steel?
Yeah, I think the challenge is the same as was mentioned by previous work, which is middleware. Compared to welding aluminium, the tool the toolware is faster when involve steel as the material. So in order to do that, I have offset the tool to be 1 millimeter towards aluminium to at least reduce a little bit, but still that just reduce, it doesn't avoid uh, overall tool weight. So that's the challenge.
Okay, that's all. Thank you, Zul, for the presentation. Okay, next I would like to call
Dah untuk yang lain. Kalau saya dah untuk yang lain.
Baik.
Dalam Google Drive tadi. Saya baru Dr. punya.
saya baru
Dr. punya drive tadi. Tak bagi.
saya nak bagi Muntaka dulu. Last kali saya bagi. Okay, I would like to call Muntaka Musa to present his work. Muntaka, are you going to use the PDF file or you want to use the PowerPoint format? Yeah, because I do only have your PDF file only. Yeah, you have submitted. Oh, okay. Okay. Okay, Taka is in his first year PhD. He's doing on digital or features construction in the 3D printing. All right, I think this is part of his work in the first year study. All right, therefore I would like to call for the Taka to present his work. Yes, please.
Thank you, sir. Assalamu alaikum. Hello, everyone. As Dr. highlighted, my name is Murtaga Musa. Going to present my paper titled Digital Reconstruction of Plastic Gear using 3D scanning technology. This is the workflow chart I have arranged, starting from introduction, objectives, up to the references. Then introduction. So the issue of 3D scanning has to do with computer-aided design software and other advanced materials. So this computer-aided software allow engineers, designers to create, initiate, and analyze 3D models. So in order to achieve common purpose. So this technology can be found in various disciplines, such as reverse engineering, arts, design, and other areas, related areas. So the paper outlined practical application of this advanced 3D scanning technology. That's to reconstruct the gear, a plastic gear. Here are the objectives. Number one, to explore 3D scanning, enhance reconstructing plastic gear through G-code, so as predicted parameters. These are plastic gear are base components that transmits the motive of motion of power which rotate the shaft. So in reconstructing these gears, it needs tasks such as repairing the damaged ones or to create new ones. So the parameters here, which G-code is expected to dictate, is the dimensions of the features and the types of the plastic that's used in production the materials inside the plastic gear. Then the second one, to assess accuracy, integration feasibility, enhance efficiency, and compare with the original model. That is to find out the perfection of how the 3D scan model is conducted. Then has to do with the improvement in efficiency, so that at the end it compare the 3D digital scan and the physical model. So what I mean by integration feasibility, here there is need of incorporation that has to do with the resources, time frame, and the organizational capabilities to achieve this. So it is to show that it is feasible to conduct the 3D scanning technology. So if not achieved, it means there is need to explore another solution to push ahead. Problem statement. We all know the world is now moving fast in terms of technological developments. So relating this issue, it is observed that traditional gear construction is outdated. Why? Because it is time consuming and there is no accuracy apart from the labor intensive. So with this, that is need to show the enhancement in digital approach due to the significance of this plastic gear. So the challenges here, wherever what happened, can be addressed with this 3D scanning technology, right? So we're using the CATIA file software and other advanced materials. Background. So many scholars have observed and stated the origin of this technology. Some mention that it was emerged in the latter half of the 20th century. And in 1990s, the advancement in geometric processing for 3D technology were pivotal in driving the progress in 3D scanning. The Leo 2020 observed that it has consists of two categories, which the first one is model-based 3D reconstruction. This involve utilizing of the existing models of the object. That has to do with ray tracing. That is the interaction of the light with the objects. So this will assess the detail of the features and the dimension and the color of the model. Then the second one is image-based 3D reconstruction. So this one has to do with single or multiple images which can be used to reconstruct 3D scene. Then the concepts of 3D scanning, many definitions are given. To summarize this, 3D scanning is a structured light scanning that is effective for producing functional products. So this is to see the major issue in this work. It is lighting condition. So without lighting condition, that is such as or to say laser triangulation. So there will be no 3D scan because it is a essential aspect of the scanning technology. Then application for this scanning can be found in many fields such as design, as I mentioned earlier, reverse engineering, and measuring complex and surfaces, etc. That photograph, it can be seen the optical 3D scanner is projecting the physical model there in order to capture the detail of the data. In any work or project of such nature, there must be challenges. So these challenges mentioned here are 5 or 6 as at least to summarize. There are many challenges. Let me explain using the next slides where it can show all the stated challenges there. So the cause of these challenges is the usage of the old version of the 3D scanner. I observed that this 3D scanner in the lab were purchased since 2018. So in the process of doing the scanning, after well prepared, that has to do with the setting conditions. That is the stand-based, the 3D scanner, and the desktop. By my left-hand side, you can see the connectivity there, where the model is fixed on the stand base in order to avoid shaking or movement, which it will affect the scanning system. So the second one in the middle, if you can see, it is a 3D scanner with the lighting condition, as I have said earlier. So projecting direct onto the model so that the features, the dimensions can be captured, which are the details that can be transmit or transfer into digital, that is 3D coordinates. These coordinates has to do with the numerical values, which stand for X, Y, Z, which highlighted or show the horizontal, vertical depth or distance of the model. So the desktop is, you can see it is there, which parameters can be used to control the scanning technology. So use the scan digital model here. Let me start by the lower one, that's figure 2A. So you can see the original color of the plastic gear and form of the shape of the plastic gear. So the overlapping and the issue of the missing surface can easily be foreseen or traced there, if you can see. So then the second one, if you observe, there is difference which shows the differentiation in the color. Why? Because of the problems encountered, and I suspected the limitation of the lighting condition of the scanner. So I improvised the normal baby powder, which is white in color, and the brush, which then I applied direct onto the physical model so that maybe the lighting condition will look very sharp if projected direct to the model. So in the process of doing it, I tried my best to see that these challenges are overcome, but yet you can still see some negative effects. Look at the down, the second one, figure 2B in the middle. You can see the some areas, there's some unwanted particles, which as a result of the inability to capture the detail of the physical models. So it appears like this. So you can see the gaps, both the figure 2B and figure 2C. The benefits of 3D scanning. There are three major importance of this 3D scanning. There is accuracy, speed, safety. So not only 3D scanning, whatever project you are conducting of such nature, there must be accuracy in order to excel. If no accuracy, no appropriate or reliable measurement, it means a problem. So the speed is save time and the cost. So it is faster than traditional. Other benefits, there is a easier capturing of the objects if compared to traditional approach or the ways that this technology are handled manually. So many objects can be used to make a uniform designs. So the advantage of the technology is overemphasized if compared to the traditional approach. Materials and methods. These are the equipment and other materials I have used like I have said, the 3D scanner that I use, you can see the technical specification by the right-hand side, the category, which is the desktop. So there is two major 3D scanner. One, it can be used that is without using exercise, handheld or wireless. So you can use to produce many models with it. And it is easy to handle. But this one, it can not be moved anyhow. So it has to be operated inside the lab due to its nature. The technology, like I have said, of this scanning process is laser triangulation. The maximum resolution and the accuracy, you can see 0.1 mm and 0.125. Then the acquisition speed of this scanner, it can operate or trace 50,000 points per second. So the dimensions are there, the weight, texture, and color, and connectivity. So this is the old model, because the price you can consider, if you can look at the price, it was over $2,000 during that time when it was purchased in 2008. Sorry. Then the brush and the baby powder can be seen, which I improvise in order to tackle the problems. So the real, that is the physical model, it is shown in figure 3D. So the diameter is 68 millimeter and the thickness is 43 millimeter. So these are the methodology. The first one is when you have the physical model, is to be well prepared before embark on this project. It should be plain. All the particles and other rubbish should be cleaned thoroughly so that it will not affect the scanning technology. Then calibration of 3D scanner. So the scanner needs to be positioned, well positioned and adjusted, because in any slight mistake, it will affect the technology. There is a scanning process. The procedure, I think I have mentioned this idea earlier, is the structured light condition that can capture the 3D scene, the coordinates, then the data acquisitions. So when the scan model is conducted, so there is need to collect the data, check the material, check the dimensions and the accuracy. So then it will be set for the digital reconstruction. So with the use of the 3D scanner and the desktop, the software you can be able to continue with the constructions as highlighted as some areas before. Then there is need for the refinement. After constructing the 3D image, like 3D scene, then as it has shown here, sorry to put here, this figure 2B. So there is need to use the tools which you can adjust the dimension and clean all the remnants, that is the unwanted appearance of other affected areas. Then the quality control. This quality control has to do with checking of the accuracy and the dimension, the textures and the color, then compare with the physical model. Then after finish all the process, then it's set to export into the digital model. This file is called serializography, that's STL file, where you can export it, move or forge ahead for the final refinement before the production of the physical model. So by my right-hand side, you can see the scan model. So it's look incomplete because of the challenges I encountered. Inshallah, effort is being made to rectify all these challenges. So after I finish, then the work it will be set for printing the physical model using the 3D printer. Parameters. These parameters representing lighting, as I said, without this lighting condition, it will not conduct it. The essence of using these parameters, object that has dark areas, so there is special setting for proper capturing of the affected areas. Is this should capture appropriately if this that is set as expected. So the neutral is baseline. It has to do without bias of the dark or light. Whatever appearance the model has, neutral can capture it very well. Then the light areas, this one is about the brightness of the physical model. So with the light, this can be captured clearly. In conclusion, this study highlights the roles of achieving effective 3D scanning technology as you observed previously. So with this CATIA 5 and other materials, it demonstrates the importance or the significant effects and its potentiality. So the technology is 3D scanner is one of the drivers of innovation, efficiency, and quality in both academic institutions and the industries. Recommendation. So let me summarize this. Under recommendation, there is need for investment in training and education because this will allow the professional to have skills which has to do with the using of latest innovative advanced materials. So there is need to further extend this in all levels so as to be alongside with the modern technological developments. Then the collaboration and knowledge sharing. The issue of collaboration is very, very important because it is where the experts within and outside can meet and have a kind of cross-fertilization of ideas, share views, share ideas, which can be used and utilized the modern innovation or initiative. More especially, this has to do with the softwares and other facilities. So integration of industry standards, there is need to standardize the scanning technology, the use of the softwares within the industry or the academic institution, accessibility and affordability. Let it be affordable to reduce the cost of the materials. Let us initiate assist in implementing the innovative materials. Then environmental consideration. So it is very, very important to consider the environmental impact in 3D scanning technology. Why? There are so many issues that can be arise, like carbon emission. This carbon emission has to do with the environmental pollution. So any problem that can lead to the pollution of the environment that's associated with the 3D scanning technology should be considered before embarking it. Then the waste materials, to minimize waste materials. There is need for the bringing such waste products in form of recycle. So this is to show that if there is initiative in recycling these products, the waste will be minimized. So acknowledgements. Sincerely speaking, I have to acknowledge the effort of my current government because of the current recession and the highly competitive issues has to do with the sponsorship. So I have to acknowledge then my able supervisor, Dr. Ahmad Baradin bin Abdullah. So I thank you all. Thank you for encouraging me. Assalamu alaikum. So I have passed the time.
Okay, thank you, Muntaka, for the presentation. Okay, any question from the floor? Yeah, Gobi, any question? Okay, my question is that how this innovation can contribute to society, especially in this case, the reconstruction of this part. So how it can contribute to the society?
Thank you for the good question, sir. This technology, there is no doubt it will contribute to the society. You remember when I said the traditional approach, which is outdated. So with the coming or the advancement of these innovative materials, a lot of ideas, a lot of new facilities can be used or utilized so that it will be easier from both academic institutions and the industries to handle these issues, particularly when it is about the technology. So if students or if experts from both sides, that is from the institution and the industry, come together, as they said, two heads are better than one. Always share the knowledge so that this knowledge can be imparted to the younger one, more especially the student, and this can be extended. Let me start the example by myself, sir. So originally, my field is arts. So I have nothing to do with the three-dimensional before. So if not because of the data that encouraged me to come to this institution, I will not come. So this is the part of the contribution. Thank you very much.
Okay, okay, thank you, Mutaka, for the presentation. Okay, the next presenter is Jiang Aimin from China. I think if I'm not mistaken, it's Conan. So I would like to call Jiang Aimin to start his presentation. Are you ready, Aimin? Oh. Okay, you can start when you are ready.
It is my turn.
Okay, I mean,
Yes, yes.
I mean, we can start when you're ready.
Okay. Okay. Hi, Doctor. Can you see my screen? Is it okay for you to see my screen? Okay. Thank you. Hello, everyone. It's a good opportunity to make this to join this research seminar organized by Professor Dr. Baha. I very appreciate this. So for the topic that I going to share, it's about the lightweight design of robotic arm that I'm going to use in my PhD research. Since the research that I'm going to do is based on the robot's arm, the name of the technology that I'm going to use is Y-arc additive manufacturing, and actually it's a compilation of robotic arm and welding machine and other control systems. So for my topic of this lightweight design, it's Inspire based. Inspire is a kind of module from software. Its name is RTail. RTail. Actually, this software is a very good tool which can be used to make lightweight design. So for the topic that I'm going to show you, that include several parts. Its structure is similar to the structure of a journal paper, which actually includes introduction, material and method, experiment, results and analysis, discussion, and conclusion. So for the first part, it's introduction. So the robotic arm that I'm going to design is actually a very common industrial mechanical arm. It's becoming growing popular in all kinds of industrial areas. But actually, as the development of robotic arm, its structure become complicated and more weight than before. So it's an urgent thing to control the weight or do some lightweight of the robotic arm to make it meet many different kinds of production situation. And actually, there are two elements when considering lightweight design. It's replacing traditional materials with lightweight with light material like aluminum and titanium. And second aspect is to use optimization techniques to get a better structure of the arm. And the way that that are used in this topic is the second one, to optimize its structure based on certain tools, and it's Autel Inspire, which you can see from here. Which you can see here. It's Autel Inspire. That's the key tools that I'm going to use in my research. This software is a good tool to ensure the mobility and the load-bearing capacity of the robotic arm when reducing its weight and enhance its machine responsively. So for the material and method that I'm going to use, actually also based on this software. It includes 3 steps. By the first step is by altering certain design factors. Optimal design seeks to guarantee that the product fulfill process restrictions and attains predetermined performance goals. So this kind of procedure allows the product to operate its intended level. But there are certain constraints which need to be added during this process. So the second one is topology optimization. It's a kind of optimization way to get a proper shape or structure for certain tools based on certain applications. The third one is this tool is capable of carrying out a global optimization of every component in the mechanical system and targeted local optimization of pertinent portions of the component. And it can execute 8 individual parts and entire mechanical system. So it's good tools to conserving materials and improve its structure condition. So for the model that I'm going to show you, which you can see from this slide, it's actually a simplified robotic arm, actually based on the robotic that I'm going to use. So generally, the robotic arm includes several parts. The first part is the substrate, and the second part is the large arm, and the second, the third part is the mid arm, and the last one is the small arm. So for the optimization object for me is the middle arm of robotic, which you can see from here. Actually it's this part that I'm going to optimize. Since there's certain constraints which need to be added when using Autel Inspire, and material is one of them. So for the material that I'm going to compare in the in this object, in this subject is aluminium 2A12 and aluminium 7075. After compare the mechanical property of these two materials, I choose the second one is aluminium 7075 dash T6. Actually, these two materials actually very common in the material that have been used in making robotic arm. And there are other things like simulation experiment that that need to actually it's also kind of constraints need to be added when using Autel Inspire. Actually, the equations of this constraint includes 4 areas, and the first one is a general equation for each A. Second, third, two dimensions of variables that need to consider, and the fourth one is the variation range of of X. And after this, then you can see the whole process of these projects includes parts model and material support and load constraints adding, then continue the following processes. And after this, there's primary strength analysis, which will be done. Then it's qualified. Then I will do the following processes like design space and shape control parameters and objectives, and topology optimization. And the results will be compared to different kind of situation, and then get the final result, the optimal result of the optimization process. So from this slide, you can see what I'm going to do is to import the module that the model that I made by Creo 7.0 and then import it to the Hotel Inspire. And I will choose certain areas that are going to be optimized. I mean to optimize its shape and its material, which means certain the colors. I mean the gray areas are the areas that are going to be optimized. But this area and this area will not be optimized. I mean, the shape and materials of these two areas will not be affected or be optimized. And after this, I need to set up materials and units, which you can see from here. Okay, yeah, it's great. Yeah. And after this, I need to set up a design space and shape control, which also be mentioned in the flowchart in the last slide. Actually, these two steps is very important to control the optimized result. For the design space, which I actually mentioned, the gray area will be changed to certain situation to meet the optimization goal or objectives, and the shape control, which we make it change, which we make this area change according to something like symmetric, like this. And after that, the strength analysis will be the original analysis will be done, which you can see from here. The displacement and von Mises stress can be shown from this picture. And after the stress analysis, which I will do, I will proceed the optimization process, and then the results will be shown like this. And after geometric reconstruction, the final results will be like this. Actually, okay. These two areas based on different kind of setting of shape control and material control. So after this, the stress calibration will be done after we get the optimized result. So after all that of experiment, simulation experiment, then the data of that processes will be gathered in these two tables, which you can see. The first table is strength calibration, which you can see from here. The first aspect is masses. It will be reduced from 11.596 kilograms to 4 kilograms. And actually, skin 1 and skin 2 are also share the same situation. But actually, skin 2 is a bit more weight than the skin 1. here is skin 1, here is skin 2. You can see there's a lot of a little bit different between these two skins. And there may the maximum warm misses stress also a little bit different. Although skin 1 and skin 2 the maxes of warm misses stress is a little bit larger than the original one, but actually it's within the safety condition. And include the shear, the max shear stress and max displacement. So for the model analysis, which you can see from here, from first model to sixth model, the frequency of them shows increasing trend, but all of them are in with the condition that can be accepted. So after all this, I guess some conclusions which you can see here. The big arm of a robotic is very important for robots to work properly and smoothly. So its weight, it's one of the big objectives need to be optimized. The second one is Altair Inspire is an option to get the optimal model parameters of a certain unstructure. And this third one is after this topology optimization, the weight of arm decreased by about 70%. So it shows unique advantages when doing lightweight design. Okay, so that's all for the things that I'm going to show today. Okay.
Okay. Okay, yeah, thank you for the presentation. Actually, this is not his project. This is just for sake of the seminar. His project is about wire arc additive manufacturing, repair on repair on parts using wire arc additive manufacturing, and we are employing the AI in order to develop the system. All right. Any question from the floor? Any question from the floor? Okay, if there is no question, I think that's the end of the morning session. Hopefully, the lunch is ready. We will continue in the evening at 2:45. We will continue at 2:40. Sorry. So thank you, Jen Amin, for the presentation. Okay, we will continue at 2:40. Or hopefully we can run earlier, 2:30, so that we can start 240, where Wazarira will present the works on recent finding of her works, and followed by a few of my FYP students. Okay. With that, I think that's the end for the morning session. We continue in the evening. So everybody, please have a lunch walk banquet room at the side. This is my side there. So okay, that's all. Thank you. See you in the afternoon session. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.